Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 2, Organic Chemistry 2. Today we will continue on chapter 1, Conjugated by Systems and Pericyclic Reactions. In the previous lecture, we have covered classes of dienes, conjugated dienes, molecular orbital theory, electrophilic addition, thermodynamic control versus kinetic control. Today, we will talk about introduction to pericyclic reactions and Diels-Alder reactions. Pericyclic reactions. What are these reactions? They proceed by a simultaneous concerted series of bond-breaking and bond-making events in a single kinetic step, often with high stereospecificity. The reaction involves a ring of electrons moving around a closed loop. The reaction occurs through a cyclic transition state. These are relatively unaffected by solvent changes, so they don't have ionic intermediate or radical. They have single neutral transition state. The three types are cyclo-addition reaction, like Diels-Alder reaction, again in a closed loop, attack, forming pi bond. So as we can see here, we have one pi bond, two, three pi bonds. We end up with cyclic compound with only one double bond. So we lose two double bonds and form two sigma bonds. In electrocyclic reaction, again closed loop, cyclic transition state, to form, we have here 1, 2, 3 pi bond. So we lose 1 pi bond. So we lost 1 pi bond, and we formed one extra sigma bond in here. In sigmatropic rearrangement, we lost this one sigma bond, but we formed another one. So we ended up like we are not losing bonds or forming bonds. It's like equal. Diels-Alder reaction. It's called 4+2 cycloaddition because a ring is formed by the interaction of 4 pi electrons in diene and 2 pi electrons in alkene or alkyne. Here we have one, two, three, 4 pi electrons, and here we have 2 pi electrons. We call this diene, and we call this dienophile, lover of diene. It's usually alkene or alkyne. could be triple bond, and this reaction needs energy for the activation. Well, when we react diene with dienophile alkene, we get cyclohexene. When we react diene with dienophile alkyne, we get 1,4-diene, cyclohexa 1,4-diene ring. The Diels-Alder reaction is like a nucleophile electrophile reaction. The diene is electron rich and the dienophile is electron poor. Simple dienes such as butadiene are sufficiently electron rich to be effective diene for the Diels-Alder reaction. However, the presence of electron donating groups such as alkyl or alkoxy group may further enhance the reactivity of the diene. So we have here diene, we have alkyl group to enrich this diene with electrons, pushing the electrons, and we have dienophile acrylonitrile with cyano group or nitrile group, electron withdrawing group. So this is electron deficient group of pi clouds. This electron poor because of the electron withdrawing effect of the cyano group. With heat, we get the adduct 3,4-dimethyl cyclohex 3-ene 1-carbonitrile. Some examples of the trend in reactivity of dienophiles and diene. Remember, electron withdrawing group dinitrile make the dienophile electron poor more and facilitate fasting the reaction. So this is much more faster than this, than the trifluoromethyl unsubstituted is faster than the methyl 1. In the diene, we have found that the alkoxy facilitate, because it's electron releasing group, pushing the electron toward the diene system, make it electron rich. So this one is faster than the one with 2-methyl, and the 2-methyl better than 1-methyl, and the 1-methyl better than unsubstituted buta 1,3-diene. So the reactivity actually increased this way. The double bond in nitroethene is electron poor, and that in methoxyethene is electron rich. Explain using resonance structure. Of course, nitro is electron withdrawing group. When we draw the loose structure, we have here electronegative element sucking the electrons, so we form double bond in here and break this double bond to form here a negative and positive here and positive here, which means that the bi system will be electron deficient. In electron donating, these two electrons will form a double bond. These two electrons will move to the terminal carbon having this negative, so they enrich actually the alkene with electrons, so it's electron rich. Moderate temperature favor the formation of products in Diels-Alder reaction, but very high temperature, over 200 degrees Celsius, tend to disfavor the product formation. In fact, in many cases, high temperature can be used to achieve reverse Diels-Alder. We call it retro Diels-Alder reaction. So we have starting material, diene and dienophile. We get a transition state, as you can see, neutral. Then we get a product. If we have high temperature, then the reaction will go on the other direction, forming once again starting material. So diene, dienophile, Diels-Alder. The other way around to cyclohexene. High temperature, we go to retro Diels-Alder reaction, and we get from cyclohexene, alkene, and diene. To understand why high temperature favor ring opening rather than formation, recall from thermo part. In organic 1, we talked about delta G equal delta H minus T delta S, where the delta H is enthalpy term and the minus T delta S is entropy term. The sign of delta G must be negative for equilibrium to favor product. Delta G must be negative. In our case, we have in the starting material 3 pi bond, okay, are broken and replaced by 1 pi and 2 sigma. Sigma bond is stronger than pi bonds. Sigma bonds are stronger than pi bond. We have 3 pi, we ended up with 1 pi and 2 sigma. And sigma is stronger. So this means that this reaction is exothermic reaction. Delta H enthalpy term will be of negative charge. Let's see the entropy term. We started with 2 molecules, diene and dienophile. We end with 1 molecule. So this means that entropy will be negative value. We started with 2. We restrict the probability because we have 1 molecule. So delta S will be always negative. But we said entropy term is minus T delta S. If delta S is negative times negative, so this value will be positive. At moderate temperature, entropy term will dominate and the total sign of delta G will be negative. At very high temperature, measured in Kelvin, this value will be high positive and will be in charge, and the delta H minus T delta S will be positive. If delta G will be positive, this means that the reaction will go the other way around because it's disfavor the product of cyclohexene. Well, in order delta G to be negative, entropy term must be larger than entropy. Okay? in very high temperature, the entropy term will be large and will dominate the enthalpy term, and delta G will be positive. If delta G will be positive, then we favor retro Diels-Alder reaction. Stereochemical requirements of Diels-Alder transition state. We have to have the diene in S-cis conformation, so the cyclopenta 1,3 diene is faster in Diels-Alder reaction than the 2,3 dimethyl buta 1,3 diene, and that is faster than the trans 1,4 dimethyl buta 1,3 diene, faster than cis 1,4 dimethyl buta 1,3 diene, and this compound, which has two double bonds trans to one another, no Diels-Alder reaction could take place. The Diels-Alder reaction is syn addition with respect to both diene and dienophile. The Diels-Alder reaction is stereospecific, which means that Diels-Alder reaction with two different isomers, like the one here we have here, 1,3 butadiene react with the cis dienophile, will give product. If we started with the trans one, we get different product trans. So here we have the cis and we have trans. Okay, so when the dienophile is 1,2 disubstituted alkene, the reaction proceeds with stereospecificity. Specifically, a cis alkene will produce cis disubstituted ring, and the trans alkene produces a trans disubstituted ring. Predict the product of the following reaction. So what we have to do is just imagine the reaction will go this way, formation of the transition state, the two cyano in different directions, and the product is trans. The Diels-Alder reaction is regioselective. When non-symmetrical diene react with non-symmetrical dienophile, two regioisomers are possible. So if we react here E1-methoxy buta 1,3 diene with methyl acrylate, we expect to get 1,2 adduct, where the two substituent will be 1,2. We call it ortho, adjacent to one another. We found that this is major, and also we could get this 1,3, we call it meta, and that trace or minor product. When we get the 2-methoxy to react with the same molecule, we got the 1,4 as a major, para, or 1,3 as minor or trace. Why is that? Why this reaction give one major than the other one? So to rationalize that, think of diene as a nucleophile and the dienophile as electrophile. Regioselectivity results from combining the most nucleophilic part of the diene with the most electrophilic part of the dienophile. When we have the methoxy on one, resonance structure will locate the negative charge on this carbon. And for the dienophile, the electron withdrawing group of the ester part will get the positive charge on this carbon. If we combine these two species, will react when we combine the negative and positive, right? So the measure will be from the approaching of these two species together. So positive here, negative here, this and this carbon will be 1, 2. When we have it in the methoxy on carbon number 2, the negative charge will be on here, okay? And the positive charge again, because of the electron withdrawing group, will be on that carbon. If we get these two species together, we have to put them on that this way. So negative will approach the positive. So the product will be 1, 4 para. See you next lecture.